Going to continue with logarithms. Okay, talking about logarithms. So logarithms are the inverse of an exponential function. So if we have the function a to the x power, the inverse of that would be a logarithm. So if I look right here, I have how we describe it or how we talk about logs is f of x equals log base a of x. So again, the three parts are log base a of x. And you could, again, because they're inverses, you could potentially change or manipulate it so that it can be rewritten as an exponential function. Again, we can think of f of x like y. So let's go ahead and try that with an actual example. So let's say that I have log base 2 of x. Well, I know that I could rewrite log base 2 of x. I could rewrite that as like saying 2 to what power equals 32. And if I'm thinking, okay, 2 times 2 times 2, that's 8. Times 2 is 16. That's 4. Times 2 is 32. So this function, log base 2 of x, when x is 32, so log base 2 of 32 equals 5. Here I'm looking at log base 4 of x when x is 2. So again, if I were to plug that in, I like to change it into the exponent form. So again, it would be 4 to what power gives me 2. And that would be, again, kind of like taking the square root of 4, which is 2. That's like saying 4 to the 1/2 power equals 2. So what does, in this case, what does f of 2 equal? Or log base 4 of 2, it equals 1/2. 4 to the 1/2 power equals 2. Some properties of logarithms. Again, how do we manipulate? How do we move these things around? How do we use them? If I have a log, if there's no 10, if there's no number below, you assume it's a 10. So if it's any other number besides a 10, it's that number. But if there's no number, you assume it's a 10. And when I have a logarithm raised to an exponent like this, I can move the exponent out front. Kind of similar. Let's go down. So log, and in parentheses, I have a multiplied by b. I can split this up into two terms. And when I have multiplying inside of my log, it's like the same thing as adding. And very much kind of on the same idea, in the same thought space, is if I divide two functions, if I divide two things inside of my logarithm, instead of adding them, I'm going to subtract them. If I have an exponent like this, again, I could rewrite this. So I'm going to move it out front. And I'm going to say 7 log base 5 of 5. And it actually works out that when you have base 5 to the same number,
and 7 times 1
is 7. It is actually going to cancel out. So really, these two cancel out each other, and or they turn into 1. 7 times 1 is 7. All right, let's try something kind of similar on this next one. I'm going to say, first off, I'm going to move this exponent over here, 5 log base 2, and then again, it's to 8, log base 2 of 8. Now, 8 is interesting because if I have 2 to the first, it's 2. 2 squared is 4. 2 to the third equals 8. So what I'm going to do is I'm actually going to rewrite this as 5 log base 2, and I'm going to rewrite 8 as 2 to the third, which again, like we just talked about above, when I have the same thing, it's going to cancel out. So really, I'm left with 5 times 3, which is going to give me an answer of 15. All right, one more example. Going to kind of do something similar like we just did, but going to break it apart. Again, because I have multiplying, I can rewrite this as 2 logarithms, and I'm adding them together. And if I just extend this one more step, again, 2 to the 4th is 16. So I'm going to rewrite some stuff just like I did before. All right, and now we're going to get that nice canceling out. So this, in fact, actually equals 7. All right, let's keep trying. This one's going to be very similar. Notice it's got a log base of a 3 this time. So again, when I split them apart, I'm going to add them, and now I'm going to say, all right, well, I got to think about my 3's. All right, so I actually am able to rewrite these. I've got log base 3. It's 3 raised to the 3rd power, gives me 27, plus log base 3 of 3 raised to the 4th power gives me 81. I got some nice canceling out here, and this also equals 7. Huh. All right. This one is not multiplication in the middle, it is division. So again, if I think back, all right, division, I need to split them apart and subtract. So I'm going to rewrite as log 4 of 256 minus log 4 of 64. Side work, 4 to the 1st, 4 squared, 4 to the 3rd. Again, you can use your calculator, but some of these you may start to just memorize. Because again, you end up using them. I'm going to rewrite this as 4 to the 4th minus log base 4, 4 to the 3rd. 4 minus 3 this time gives me 1. So I'm going to say, all right, we've got division, so let's split them up. All right, now that I've split them up, again, I'm going to potentially think about, is there anything I can rewrite? And we know that 2 to the 3rd is 8, and it's actually going to be 2 to the 7th power. So once I get 64, 2 to the 6th, then I get 2 to the 7th is 128. So I'm going to rewrite 2 to the 7th minus log base 2, 2 to the 3rd. Again, when I cancel these out, I get 7 minus 3, which is 4. First thing I see on this one, I'm going to move my exponent out of the way. So I'm going to move it all the way over here in front. 5 log base 2. Again, this part hasn't changed yet. Now you could multiply it, but again, you're going to get some numbers that are harder to work with that you might not know what those square numbers are and stuff. So let's go ahead and use our rules and split apart. So the first thing I see is I've got multiplication on the top. So I'm going to split this apart, keep my 5 outside, and I'm going to say, I don't need it quite so big. I'm going to say log base 2 of 128 plus log base 2 of 64 minus, because I'm on the division part, log base 2 of 8 minus log base 2 of 16. All right, keeping what's outside, now I'm just going to try to simplify. We already said that this was 2 to the 7th, and again, that's going to cancel out, so it's going to be a 7. This is 2 to the 6th, so again, that's going to cancel out and give me 6. 2 to the 3rd minus 3, and 2 to the 4th minus 4. So first thing I see is, hey, I've got positive 7, negative 7, that cancels out. So I just am left with 5 on the outside multiplied by 6 on the inside, which is going to give us an answer of 30. All right, looking at graphing logarithms, okay? So again, I'm thinking about graphing y equals log base 5 of x. So again, looking at sort of the change, how we can change the base, or another way we can think of it is I could rewrite it as 5 to the y power equals x. And so what I'm going to do is I'm just going to pick some values that I know with my y value so that I can determine what the x is and then potentially maybe graph that. So 0, 1, and 2. So again, I'm looking right here at 5 to the y equals x. And so if I were to plug in a negative 2, I'm trying to think, where should I do the work right here? If I plug in, so 5 to the negative 2 power, what would that equal? Well, I know because of my exponent rules, it's 5 squared, it's 25, but because it's negative, it's getting smaller. So that would be like saying 1/25. And as a logarithm, again, if I were to plug it in like that, now I would say log 5 or log base 5 of 125 equals negative 2. All right, so I'm going to plug in 125 here. Now I'm going to try to look at y is negative 1. So again, I'm using my formula y to the 5 to the y power equals x. So I'm going to say, okay, let's try 5 to the negative first. Again, I know that that's going to equal 1/5, just because 5 to the first is 5. Okay, and then if I were to write it over here, I would say log base 5 of 1/5 equals negative 1. And so I'm going to plug in a 1/5 in my table. All right, continuing on, 5 to the, we're going to plug in y to the 0 power. So again, 5 to the 0. Well, we know that anything to the 0 power is 1. So again, if I were to write that, that would be like saying log 5 of 1 equals 0. We're just going to move our work over a little bit and jump right here. All right, now I'm going to say 5 to the first. Again, I know that that's 5. In log form, that would be log of base 5 of 5 equals 1. We know that that would cancel out. And so that's going to be 5. And my last one is 5 squared. Again, 25. That would be log 5 of 25 equals 2. And that's going to be right here. So now that I've got these sort of values of my in my table, I'm going to go ahead and potentially try to graph that. So first I'm going to mark, all right, here's 0. Here's, let's move it a little bit. Here's 1. Here's 2. Here's negative 1. Again, I'm plugging in those y values. Here's negative 2. Let's maybe say that this is 5, 10, 15, 20. I know we're getting close to the end here, 25. Not quite exactly to scale, but that's okay. So my first term, x is negative, or x is 1/25. That's going to be very, very close to 0. And its y value is negative 2. So that's going to be all the way down here. So logarithms actually are going to create an asymptote, as we'll see, because when I go to x is 1/5, that's a little bit further out, but still not, I wouldn't say still very, very far on our graph. Y is equal to negative 1. And then I'm moving along a little bit. I get x equal to 1 and y is equal to 0. So let's put that right here. And then I get x is equal to 5 and y is equal to 1. That's going to be right here. And then I get x is equal to 25 and y is equal to 2. So I'm going to put that all the way over here. So when I go through and connect the dots, I'm kind of creating a graph that looks something like this. And again, this is going to create an asymptote. This line will never cross. We're going to call this when x equals 0. Okay, this line x equals 0, it is never going to ever cross. So again, one way we could say that is the domain is greater than 0.